Here we will analyze continuous beam subjected to uniform distributed load. So for that you have to change directory to your current directory. So for me this plate directory is selected, so all the temporary files will be stored there and whatever you save will be saved in that folder. So in the preferences you select structural, okay. Then you start the preprocessor. In the preprocessor, first element type, so add edit element type, so add, and our element is beam element, and we select the 2 node 188 beam element. There is a 3 node 189 and 2 node 188. That means the number of the beam element is 188. Okay, then close. Now element type is done. Material properties. In material properties, material models, structural, linear, elastic, isotropic. So this is, I am taking as 2E5, that is 2 into 10 to the power 5 Newton per millimeter square. I am taking Newton as the unit of force and millimeter as unit of length. And remember, we have to be consistent with the units. Though Poisson's ratio is not required, but still we are giving a value of Poisson's ratio, otherwise it will issue a warning. So okay, so the material is selected, and then sections. So beam, common sections. So in the rectangular section actually we give B equal to 20 and H equal to 20. So it's a square section. So section is given, and now modeling. So create. So these key points, lines and areas and volumes, they are geometric entities, and you model the geometry using these. And then comes the finite element entities. Nodes and elements, they are finite element entities, and from the geometric model, by using mesh generation, you get the finite element model. So let's create key points first in active coordinate system. So if you don't give anything here, it will automatically be, if you don't give any value here, it will automatically be taken as 0, and the key point numbers, if you don't give any value, it will be automatically increased. And so for the first node, since we take it at 0 0 0, x equal to 0, y equal to 0 and z equal to 0, we are not giving any value, and we are pressing apply. Apply means it will again, this screen will again come back and it will expect the next key point coordinates. So we are giving apply, we are pressing apply, and it has again come, and here we give 400. So now okay, so now 2 key points are created, one here which you cannot show, and this you can see, which one you cannot see because it is behind the coordinate axis, and this 2 you can see. So now key point has been created. Now lines, so straight line. So now it expects you to click the key points to create the line. So straight line will be created by clicking 2 key points. So this one has been selected, so you will find its number here, it's showing key point number 1. Then you go here, once you go near this, then the line will be shown, though the line is not drawn, but once you take the mouse cursor near the point 2, key point 2, the line will be shown, and once you select it, then the line is created. Then you press OK, and a line is created. So this is our geometry. Our geometry consists of 2 key points and 1 lines, and here so from plot controls numbering, you can switch on the line numbers and you can then plot lines. You can see the line number and plot control numbering. If you switch on the key point option, then the key point numbers are also shown. So, and here this list is very useful, so you can always check whether what you have done or what you have intended to do, whether ANSYS has correctly accepted it. So key points coordinates only. Here you see there are two key points, one at 0, 0, 0, one has 400, 0, 0. Then you list the lines and it will show that one line is created from between key points 1 and 2 and the length of the line is 400. Now the geometric model is done and you go to meshing. So mesh attributes, so default attributes. So it is now default attributes means now it is taking these attributes. So since you have a single beam element, you have a single material number and you have single section number, so the default attribute is the attribute you need at this point of time. So but if there are multiple types or multiple material number, multiple materials or multiple sections, then you have to select it with which you are going to create the next elements. So for us it's okay. So now and meshing will be done. So let us use this size control. So in this size control, manual size, so lines, so all lines, there is a single line, all lines, and how many divisions you want on the line. So let us put 10 divisions. The size is not required. Once you give size, then number of division is not required. So it will create equal, it will divide the line in equal line segments because you are not giving any spacing ratio. So okay, so now it is showing that it has divided the line in 10 lines. So now the size control is done. Now mesh lines, so you have first given the size control, then the mesh lines. You can just give the line number here, you can select the line, or you can give pick all, because there is pick all means all the lines will be selected. You have only a single line, so that single line will be selected. So we are just by mouse clicking we are selecting the line, then okay. Now the line has been divided into 10 elements. So from list you just check elements, nodes plus attributes. Here you see the 10 elements, material number, this the section number, element 1, and the nodes are 1 and 3, element 2 the nodes are 3 and 4. So let us check in plot controls numbering. So here you can just keep this off now and you can give element attribute numbering, which is no numbering, so element numbers. So now we have switched on this option and okay. So now the element numbers are shown, and if you want to show the node numbers, then numbering, so node numbers on, and you can see the node numbers. So now the elements are all created. Now it's time to give the forces. So in loads, so define loads, apply structural. So it is first displacement for creating the boundary conditions on nodes. Now the nodes have been created, so you can select nodes. So this node, okay, and you fix all DOFs, all DOFs. So Now all DOFs are restricted in this node. That means it has become a fixed support. Now you go displacement pressure, you go, and here on beams. So on beams you select pick all, then all beam elements will be selected. Otherwise you can select a single beam element. Okay, so you can select a single beam element like I have selected, or you can select all beam elements. So now they are expecting one load key, that means whether the load will be in the Y direction or in the Z direction. So this is a 3D beam, so it can take load, it can take loads in the Y direction or X direction. So let us keep it 1 and give it a pressure value of 1. That means 1 Newton per millimeter load is given. The units have to be consistent. We are taking millimeter for length and Newton for force. Okay, so we are not being able to see the load. What happened? So just go to plot control, pan, zoom, rotate, and give isometric view. See the load in the other direction. So what you have to do is you have to change on beams pick all. So here keep it and make it 0. So this load will be made 0. Okay, then you plot, replot, this load is gone. Then on beams pick all, give load key 2 and pressure value at 1. So yes, now the load is rightly applied as we wish. So the load is applied, and now it's time to the boundary condition is applied, the load is applied. Now we can go to the solution portion. The solution, so analysis type, so new analysis, it is a static analysis. Other type of analysis, modal, harmonic, transient. For dynamic analysis, spectrum, eigenbuckling is the buckling analysis, and substructuring. Okay, so now solve current load step, and okay, so the solution is done. Close. The first thing you do, you go to the general post processor, and just you can just read the results. First set, the results are red, and you plot results. Deformed shape, here only deformed shape, or deformed plus undeformed, or deformed plus undeformed age. So here deformed plus undeformed. So this is the white one, white is the undeformed, and the colored one is the deformed shape, and this is the maximum deformation 1.20386. You can verify by doing hand calculation. Just PL cube by 3 EI for P. So this is a distributed load, so this is not a concentrated load, so you cannot do PL cube by 3i. So use the formula for distributed load and find out the deflection at the free end and compare it with what you get using ANSYS. Sorry, it's not PL cube by 3i. So now what you can do is you have seen the deformation, and here list results. You can go to nodal solutions, so it will give you the DOF solution. So X component, Y component, so Y component of displacement, and it will give you the displacement at all nodes, the Y component of displacement. So and this is percentage error elements. Also we can go to element solution and structural forces, or sorry, structural moments is better. So it's use the z component of moment, okay, and you get the moments in the z component of the moments at elements. So first element, node 1 3, these are the moments. So this is useful. And or what you can do is, in plot results, okay, here what you can do is element table. So you can define one element table, add. So here you can do by sequence number ANSYS, and you get 3. So okay, close. And so plot results, contour plot, line element result, ANSYS 3, okay, and it give you the moment of the left end. I suppose it gives you the moment of the right end, so, and it keeps it constant over the element. So if you make the element size larger and larger, you will get a good bending moment diagram. Actually it is the moment, so far as I remember, it is the moment at the right end, so so ANSYS 3. So you can just check, beam 188 ANSYS. So yes, so in beam 88 you just go at the bottom, yes, here they have defined my, mz bending moments. Small y and small z means local yz, and here, yes, the sequence numbers they are given. So mz is ANSYS 3 at the node, ANSYS 3 at node I. So we have given ANSYS 3. So this is how you get the bending moment. That is the node I, first node. So that means it is at the left end. So the left end bending moment it is showing and keeping it constant. So this is how you can analyze a beam in ANSYS. So let me stop here.